Okay, this question wants us to really dig deep into potential energy surfaces and label all of the information and also examine different possible pathways. Okay, this reaction coordinates represent two possible pathways from the same reactants to different products. Now, because this was a black and white diagram, that's why they're separated. But if I were to be able to draw it in full color like I can on my iPad, I could move this one over to this graph to represent, okay, we're talking about the same reactants going to a different set of products. So it really is essentially two competing pathways. So I have the purple pathway and I have the red pathway. Now, let's do some of the basic stuff. It wants us to identify activation energies, transition states, products, and intermediates. And so let's go ahead and do that. And so we've got products here. And so let's just call this products B, and let's call these products A. All right, and then we have what wants us to label intermediates. Well, intermediates only happen when there's multiple steps. This one is a one-step pathway, and this one is a two-step pathway. So there aren't intermediates in the pathway for B, but there is an intermediate for the pathway leading to A. And I think what I'll do is I'll move that down, point at it there. Okay, what about the transition states? And so there's going to be every maxima along every pathway represents a transition state. So here is a transition state. I'm just going to use the phrase transitions. I'm just going to use this abbreviation, transition state 1, transition state 2, and this will be transition state 3. And they're not, all the transition states aren't on the same path. Transition state 1 and 2 are, but transition state 3 is on a different path. Now, what about activation energies? That's just this one, it's really small. So let's look at pathway for B. There's my activation energy for B. That's EA for reactant B. And I've got a couple of different activation energies on the other pathway. I've got this activation energy. That's EA1A. And then I've got this activation energy. That's EA2A. So there's 3 activation energies. So what have I done? I've labeled all activation energies, transition states, products, intermediates, and of course, then these are the reactants. And remember, this set of reactants is the same as those reactants, and I'm just using different pictures for simplicity's sake, but they would be on the same graph in a full colored environment. So the other thing it wants us to do as being to label them as thermodynamically or kinetically controlled. And then it wants to know what conditions would favor the reaction coordinate on the right. And that's this one. So it wants us to tell us what conditions would actually cause the reactants to proceed towards product B rather than product A. Well, let's take a look at the different reaction coordinates. And now I'm thinking about the purple reaction coordinate only. Is that thermodynamically controlled or kinetically controlled? So in order to answer the question about control from the same reactants to different products, we need to consider whether the fastest reaction, in other words, the one with the smallest activation energy, and we also need to consider the lowest energy products. The one with the lowest energy products they're thermodynamically controlled. So the purple reaction coordinate is under thermodynamic control. When we think about kinetic control, what we need to think about is which one has the lowest activation energy. And we see that EA for the products leading to B is the lowest activation energy. So this one is under kinetic control. Okay, so the question now becomes which set of reaction coordinates favors, or what conditions favor the coordinates on the right? So how do we favor a reaction where the products are actually higher in energy? Well, if that reaction is kinetically controlled and we keep the temperature down, then particles can overcome the small activation barrier that leads to product B, but those particles get trapped as product B because they can't get back over the barrier. So they're able to go over the barrier this direction, but they get trapped in this well because there's not enough energy at low temperature to go the other direction. So how do we do it? We do it with low temperature. Okay, that's it.